Hi everyone, welcome back to this series of devlogs documenting the development of a co-op multiplayer heist game. In this episode, we'll cover the fundamentals of the network configuration, the in-game UI, adding security cameras, and implementing some bullet hit visual effects. In the last episode, I didn't really do a great job of covering the network configuration. It's not the most exciting topic, so I don't want to get too far into the nitty-gritty of it, but it is still very important to the game, so I'll cover that in a bit more detail here. I'm using a standard host-client setup, where one player is the host and the other are the clients. The host version of the world is what's considered to be the true representation, and the other clients will do their best to keep their versions synchronized with the hosts. In a competitive multiplayer game, all gunshots and movement would be verified by the server to make sure a client isn't cheating. But with this being a casual co-op game, I'm less concerned with cheating, so I will be allowing the clients to directly make changes to the host's world. Unity netcode has some components that handle synchronizing across the hosts and clients. The one we'll use most often is the network transform. This component allows you to configure what transform properties get shared over the network, position, rotation and/or scale, and on what individual axis. For the player transform, we will only need the position and Y rotation, because the player will never change scale or rotate on the X or Z axes. Network transforms also allow you to choose what precision they are synchronized with. A lower precision means less data needs to be sent, which will help reduce network usage and hopefully keep the game as responsive as possible. We want the player transforms to be accurate though, so we'll leave these settings as default. Normally a network transform is only authorized to be moved by the host, but Unity has some code snippets on their netcode website for a client network transform, which allows clients to have full control over their own transforms. This is a very simple piece of code, it just inherits from the standard network transform component, but overrides it to allow full client control. One of the other netcode components we will use regularly is the network animator. We will use this for our player animations. This component synchronizes the attached animation controller over the network, meaning the character's animations will look the same for all connected players. There are a few other ways the host and clients can interact. One common way is to do something called a remote procedure call. A remote procedure call, or RPC, allows one player to execute code on another player's machine. In the previous video, I used a server RPC for when a player had done enough damage to the safe and the safe door needed to swing open for all players. The UI is composed of four main areas. The simplest is the ammo counter for the currently equipped weapon or gadget. This is fairly straightforward and just controlled by some static events. So when a gun is fired, said gun also triggers an event to update the UI text label to represent the new ammo count. Next up is the player's status UI. When a player is spawned on the server, the player data script registers itself with the in-game UI script, and we subscribe to some new event listeners here for any time the player's health, name or money changes, so the UI can update itself immediately with the new values. The third area is the alert status UI. This is displayed so the player can keep updated with how the heist is going. When the heist starts, the player is unnoticed, but any time the player is spotted by a security guard or caught on camera in a restricted area, the alert status UI will change to an alert mode. The user then has a couple of seconds to get out of view to prevent setting off any alarms. If any security guard notices any odd behaviour or holes in walls where there shouldn't be any holes, they can trigger off an investigation. This will last an indefinite amount of time and will put any security on a higher state of alert. Finally, if a player is caught, the alert status UI will flash red and show the player is compromised. This means police will be called and excessive force will be used against any compromised players. The final and probably most complex part of the in-game UI is the compass. I made the individual components of the compass graphics in Photoshop and compressed them into a sprite sheet. As the compass will nearly always be moving, it makes more sense to use images for the text here, as they're quicker to draw than Unity's TextMesh Pro system. The compass graphic is broken into two halves. This is so when the camera rotates to the left, I can switch the X position of the second half so it seamlessly loops as if it's one continuous image. I also output the player's exact current rotation to help them give quick callouts to their teammates. For the security camera, I first modelled it in Blender, first creating a low poly version and then the high poly version with the help of the subdivision modifier. Then we export it to Substance Painter and bake the standard texture maps. We then build up the materials and textures using the baked texture maps as masks. To get the security camera working, I put some capsule colliders in front of the camera. When the player is inside one of these capsules, the alert status UI is triggered to show an alert, and eventually a compromised status. Whilst this works for a test, it's definitely not a final solution, as a player that might be obscured from the camera's vision by a corner or an object would still trigger the alert. So to get around this, I use a combination of a big capsule to find any players in the camera's field of view, but then I fire a raycast from the camera lens to the character's head and one to the character's torso to see if they are actually visible to the camera. For this first attempt at the bullet hit VFX, I'm going to use actual 3D meshes to show the blood. I first generated the mesh in Blender. Using metaballs, I sculpt the splat at 3 separate stages of its lifespan. Initially, I had intended to fade between these 3 individual meshes for each splat, but I found it actually looked better to use one mesh and scale it up while simultaneously making the mesh skinnier. We can make the mesh skinnier by making a shader graph that scales each vertex along its normal. This gives the effect that the liquid is dissipating in the air. I also add the option to control the opacity in the shader. I do this using dithering. It may just be that I'm getting on in years, but there's something so comforting about using dithering as opposed to regular alpha blending. I'm not actually 100% sure if I want to use this approach for blood, or whether I should go with something a bit more comic and PG in style. If you've got an opinion on this, please let me know in the comments. And that's as far as I've got for the moment. Please be sure to tune in for the next video, where we'll have some new gameplay features, some new gun models, and hopefully some sweet voxels. Bye for now.